All right, last exponent lesson, lesson 7 in unit 4. We're going to look at exponential growth and exponential decay. So some more word problems. Exponential growth. This is used to represent a situation where there is a percentage of growth during a certain period of time. Some common examples are a growing population or price increases or money, compound interest. Again, the basic equation is the same as what we've been dealing with. Y equals a b to the x, where a is the initial value and b is the rate of growth, the percent it's growing by. And for growth, this is really important. For growth, the rate of growth will always be bigger than 1. So the price of a new home is increasing by about 3% each year. So there we go. It's increasing by 3% each year. The value of a $175,000 new home can be modeled by the equation P equals $175,000 times 1.03 of the exponent x. So there's our initial value, and there's our growth rate. P is the price, and x is the number of years. Sketch a graph of this situation. So quick graph. There we go. X is the number of years, and P is the price. So quick graph, we know that it's going to start at 175. Well, I'm going to change that just a little bit. We know that it's going to start at $175,000, and it's increasing by 3% each year. So we're going to really slowly go up, because we know the shape of an exponential graph looks like that, and it's increasing, so it's very slowly going up by 3%. So there's your quick graph. What will the new home cost 5 years from now? So I take my equation, and I set x equal to 5, because x is the time, so I take out x and I put in 5. And I get out my calculator and I calculate it. So I've got 175,000 times 1.03 to the exponent 5. So after 5 years, that house should be worth $202,872.96. And we knew it was increasing, so it should be going up. It should be bigger than 175,000. And because it's increasing, it's bigger than 1. So it's increasing by 3%. So we have 1 plus 3%. That gives us 1.03, because when you change your percent to a decimal, it's 0.03. So it's increasing by 3%. What will the new home cost 10 years from now? Same idea. Take out the x and put in 10. So we've got 175,000 times 1.03 to the exponent 10. So 175,000 times 1.03 to the exponent 10. So we're looking at a value of $235,185.37. So the most important thing to understand about growth is that it is increasing. That means what you're multiplying by is bigger than 1. Let's look at another example of growth. Population of a bacteria doubles every 4 hours. The population is modeled by the equation y equals 5 to the x. There's my initial value. I'm starting with 5 bacteria. There's what I'm growing by. It's 2 because the population doubles. So I'm multiplying by 2 every time. What is the initial population of the bacteria? So we just talked about that. The initial population is 5. How many bacteria will be present after 4 hours? So you gotta be careful with this one, because it doubles every 4 hours. So it has a doubling period or a set amount of time. So if it doubles every 4 hours, after 4 hours, it's only going to double once. So if we start with 5, we double once, we're going to have 10 bacteria after 4 hours. About how long will it take to reach 10,000 bacteria? Well, if you think about it, we could figure it all out. We could double it if we start with 5. We start with 5. Whoops, let me fix that. I'm just double checking my equation. Doubles every 4 hours. So at the start, we have 5. In 4 hours, we would have 10. In another 4 hours, it would double again, and we'd have 20. In another 4 hours, it would double again, and we'd have 40. And we could keep going with this chart. If I skip over here, so I use my space, in another 4 hours, so 16, it'll double and we'll have 80. In 20 hours, it'll double and we'll have 160. In another 4 hours, and I'm just going to keep going. Another 4 hours, what are we at? 640. Am I going to have enough space or not? In another 4 hours, 640 is 1280. And another 4 hours, 25, 60, 80, 16, yep. And another 4 hours. And we keep going with that chart. I'm going to grab my calculator here. We keep going with that chart. 60 times 2 is 5120. Another 4 hours, 5120 times 2 is 10,240. There we go. How long will it take to reach 10,000 bacteria? It's going to take 44 hours. All right, that's growth. Let's look at decay. Decay is used to represent a situation where it is decreasing during a period of time. Things like depreciation on a vehicle, radioactive decay, certain substances, chemicals have a half-life. The amount left in your system of like caffeine decreases. So the basic equation is the same. The only difference is that when it's decreasing, the B is a fraction. It's between 0 and 1. So half-life is a special case where B would be a half. So let's look at an example of depreciation, of decay. Once you purchase a car, its value declines at a rate of 20% per year. Value of a $25,000 car after X years can be modeled by the equation B equals 25,000 times 0.8 to the X. So you gotta be careful with these. It loses 20% each year, but its value is not 20%. Its value is 100% you started with minus the 20% you're losing, leaving a value of 80%. And 80% is a decimal, is 0.8. And that's where the B comes from. So if I sketch a quick graph, I know it's decreasing. I'm going to start, at 25,000 value. And over time, it's going to take on that exponential shape of decreasing. What is the value of the car after 3 years? Well, 3 years is your time. Take out the X and put in 3 and figure out our value. 25,000 times 0.8 to the exponent 3. The real trick with this one is getting the 0.8, understanding the value of the car is not the 20% it's losing. The value is the 80% that's left. So I'm going to do 25,000 times 0.8 to the exponent 3, and I get a value of $12,800 after 3 years. What is the value of the car after 8 years? Take out the x and put in 8. And get your calculator out. 25,000 times 0.8 to the exponent 8. And we've got $4,194.30. So it should make sense if it's depreciating that the amount you get is less than what you started with, unlike growth where the amount you get should be more than what you started with. Second one, a certain radioactive substance has a half-life. So half-life means you're multiplying by a half, your B value, of 30 years. So that means it takes 30 years for the original amount to split in half. So every 30 years, it splits in half. If 200 grams of the substance is set to decompose, the amount remaining after X years can be modeled by the equation. So we're starting with 200 grams. Every 30 years, it splits in half. How much of the substance remains after 60 years? So if we think about it, after 60 years, it splits in half every 30. So that would mean it splits in half twice over 60 years. So we can use our equation. The years is our X. So we take out the X and we put in 60. And we'd have 60 divided by 30, and that's just like we just talked about. 60 divided by 30 would mean it splits in half twice. So I would have, once I've got my calculator up again, 200 times 0.5 to the exponent 2. So I would have 50 grams remaining after 60 years. How much of the substance will remain after 100? Same idea. Take out the X and put in 100. So 200 times a half, 100 divided by 30. So you have to be careful when you enter this in your calculator. 200 times a half to the exponent. And you're going to have to put your exponent in brackets. 100 divided by 30 in brackets. And you should get about 19.8 grams remaining after 100 years. Okay, so that was really quick. You might want to go back and pause this and write down the examples that you've got in your notes, and then you can try the questions on page 401 and 410.